All right. So in this video, I'm going to go over an example of an application example of how to use Newton's law of cooling, that model. And this example comes straight out of my actual life. So when you make yogurt, what you actually have to do is you have to take some milk and you have to heat the milk to a certain temperature. So when my wife and I were doing this, we heated up the milk to 200 degrees Fahrenheit. Okay. And then what you have to do, and this is our goal in this problem, is we have to wait. You just sit around and wait for that milk to cool to 115 degrees. And then after it's cooled to the right temperature, then you add some enzymes, and then I can't remember, stick it in the fridge or something like that. And then the enzymes in the milk then go and do whatever stuff they do and turn it into yogurt, right? So this is how you make yogurt at home from whole milk. So the way this cooling happens, when you're sitting around waiting for your 200 degree milk to cool down to 115 degrees, in order for that to happen, the amount of time it takes is going to depend on the ambient temperature. So in my house, we keep our thermostat at 68 degrees. And this occurred in the winter, I think. So 68 degrees. That's the temperature inside my room. And so the milk is just sitting in the kitchen cooling down in the 68 degree room. So when we were doing this one time, I realized as it was happening that we were about to experience Newton's law of cooling. So I took some measurements. All I did was I took one measurement, and that is I waited 20 minutes and took the temperature of the milk, and the milk had cooled to 171 degrees. So with that information alone, just that, we should be able to now calculate how long we should have to wait before it cools to 115. So the question here we want to answer is how long, or rather specifically how much longer after we've already waited 20 minutes and checked the temperature, how much longer must I wait for my milk? All right. So let's see how we can solve that. So first of all, we're going to use this model. T of t is A, where A is the initial difference in temperatures between the object, which is the milk in this case, and the surroundings, which is the 68 degrees. So that would be 200 minus 68. And then times e to the kt. K is going to be a negative number. That's going to be our relative decay rate for the cooling. And that K value basically depends on the physical properties of the materials, like whether it's milk or coffee, or whether you're talking about like a hunk of metal or a piece of wood or like a stone, a hot stone. Depending on the properties of the material and how the molecules move around and how the energy gets transferred between things, that's going to govern how fast the cooling occurs. So for example, like metal is going to cool down really quickly because metal conducts heat very easily, whereas something like a stone would cool down more slowly because stones don't conduct heat as readily as metal does. So just for example, that's what K is. It depends on the properties of the material. So we have no way of knowing what K is unless we take some measurements and calculate it. Okay, so we're going to figure out what K is, and then we're going to take that K, put it back in, and answer the question, how much longer do we have to wait? So let's go. So the first thing I'm going to do is calculate A. A is going to be 200 minus 68. So that is 132. Okay. I'm going to leave the units off for now. These amounts are all in degrees Fahrenheit. Okay, so we have A is 132. So now we know our model is T of t equals 132 times e to the kt plus 68. And we know that t of 20 minutes is equal to 171, right? Because that's what we measured. After 20 minutes, milk had cooled to 171 degrees. So what I can do is I can write 171 is going to equal 132 times e to the power 20k. That's putting in 20 minutes for time, and then plus the 68. So this is what I get. Basically, that comes from this piece of information, right? That's our measurement we made. So now I can solve this for my k. All right, let's subtract the 68. So I'm going to get 103 equals 132 e to the 20k. Divide both sides by the 132. We get e to the 20k. Then we'll do a natural logarithm. Natural log of 103 over 132 will be just 20k, right? Because the natural log will cancel out the natural exponential. Then you divide by 20. So k is natural log of 103 divided by 132, and then all of that divided by 20, and that is approximately negative 0.0124. So we have a k value, all right? Now this is going to be a constant because this is determined by the properties of the milk and the air, right? This is the decay rate for temperature transferring between milk and air. All right, so that is a constant, or at least we're assuming it is. So now I'll keep this paper around, and so if we need to look at it, we can. I'll do that actually. So now we want to solve T of t equals 115 degrees, right? Because we want to know how long, what will the time value be when it finally cools to 115. So we'll take our T of t, which is now 132 e to the negative 0.0124 times t. That's putting the k value in for k. T is now our variable, and we still have the plus 68, of course. We're going to set that equal to 115. So we'll subtract the 68. Oh, I'm sorry, 132. It's a 2 there. E to the negative 0.0124 t. It's going to equal 47. So that's subtracting 68 from 115. The next we'll divide by 132. 7 over 132. Do the log of both sides, which will cancel out the e. So we got negative 0.0124t equals the natural log of this 47 over 132. And finally, we'll divide by the negative 0.014124. So t is this divided by the negative 0.0124, and that is approximately 82 minutes. Okay, I rounded to the nearest minute. It's approximately 82 minutes. So now, given that, okay, let's scoot this up. Given that we've already waited 20 minutes, we're going to subtract the 20 minutes that we've already waited, right? Because that time has already passed. We're assuming we're doing this calculation right after making our measurement. So the 20 minutes has passed. Subtract that, and you get 62 minutes. So that's our answer. Wait this long. Much longer. And then after 62 more minutes have passed, then ideally, hypothetically, according to the model, the temperature should have cooled to 115.